space estimation, which is a nice thing to know about. And then you will kind of know the full theory that has been developed, again, over many, many years for the problem of estimation. And then we're going to do, we're going to go through an extended example. We're going to talk about signal detection theory, and it's also, it's nicely, is the same initial signal detection theory or statistical decision theory, SDT, which is a whole class of methodologies. And I'm going to concentrate on the general, the theory, the framework. And then, and Mike, next time, will do a little bit of more detailed, concrete examples of how this gets used to model human behavior.
Really?
Yeah. You didn't know that? It's easy. I'm just assuming that I will finish. I know. Okay. All right. So let's finish talking about this. So we introduced the idea of map estimation. We went through a simple example with the coin tossing, right? So the map estimation is just like maximum likelihood estimation. The difference is just that you multiply by the prior, not just the conditional distribution of your measurements, which are the likelihood functions, like a product of likelihood functions. You also include one more thing, which is the prior. And we pointed out even in the coin flipping case that the prior matters a lot when you don't have much data. It has a big influence on your estimate. But when you got a lot of data, the importance of the prior basically fades away. And you can kind of see that intuitively, because what you're going to do is you're going to take a product of a whole bunch of terms, one for each data measurement, and one for the prior. And the more data measurements there are, the more they're going to kind of dominate the end result. Okay? You're taking this product of things. If you have one data measurement and the prior, you're kind of fusing those two things. And that's the case we'll talk about in just a second on the Gaussian example. But as you add more data, you're multiplying more and more likelihood terms, right? You're taking the product of all these things. If you take the log of this, then you're taking a sum of the logs of these things. And you're basically looking for the maximum of that entire thing. And it's going to be more and more dominated by what you would get from just the data terms, i.e. you'll get closer and closer to the same answer you would get by doing maximum likelihood. Nevertheless, in cases where you don't have enough data, and in many modern contexts, we deal with cases that are high-dimensional, so it's very hard to get enough data to constrain high-dimensional problems. In one-dimensional problems, you're kind of used to this idea that you just collect enough stuff that you can basically get the answer. But in high dimensions, it's often the case that you can't even come close to that. And more in neuroscience and in psychology, this is the case as we deal with things like MRI boxes where you've got thousands of them, or neurons where you've got hundreds or thousands or millions of them. You're not going to be able to get enough measurements to squeeze down the error bars to something tiny. And it becomes important to actually include things like priors, or as we'll talk about in the next section, regularizers. That word to describe things that we do in estimation in order to stabilize the estimation problem. Okay, enough babbling, let's do this example. So what we're going to do right now is we went through this coin tossing thing. Coin tossing, by the way, the parameter you're estimating in those examples is a continuous parameter. That's the probability of the coin between 0 and 1 of giving heads. It's a continuous, it's a value that's a real number between 0 and 1. But the data are binary, right? You flip a coin, you get heads or tails, right? And then there was the Poisson case. That's also a continuous valued thing that controls the rate of the Poisson distribution. So there's a continuous rate. That's a positive number from 0. Can be any value, but it can't be negative. It's a positive real value. And then the measurements are now integers, positive integers, well, positive or 0, right? So it's integers because it's the count. And then we talked about, we did the uniform distribution one. Right? So there's the parameter you're estimating is again continuous, it's a real number, and the measurements are now real numbers. And the Gaussian case, it's also going to be real and real. So you can have all these different combinations of things where the measurements are discrete or the measurements are continuous. You can be estimating a parameter that is discrete or a parameter that is continuous. And all these things it's all the same math. It often comes down to things like, do you write down discrete cases Or do you average over discrete cases, or are you integrating over continuous values? And we'll see, we've seen already some examples of both of those things, and we'll continue to do that. Okay, so now let's do the Gaussian case for the map estimate. Right? So if you make measurements that are contaminated with Gaussian noise, and you assume a prior, because we're going to talk about map estimation, the prior on the thing we're trying to estimate, we assume a prior that is Gaussian. Then the posterior, which is the product of the likelihood and the prior, is also Gaussian. And that just, it really just comes about because when you multiply two Gaussian forms, it's an exponential of something quadratic, another exponential of something quadratic. You multiply those two things together, it's a product of two exponentials, i.e. it's an exponential where you add the two exponents, and the two exponents are both quadratic. So the whole thing is quadratic. I mean, you've seen this, right? Mike went through completing the squares. It's the same idea, right? Once you put this thing together, it's a big quadratic thing. You have to rearrange terms and turn it into a single quadratic thing. But in the end, it's still Gaussian. So products of Gaussians are Gaussian. Slicing a Gaussian is Gaussian. Integrating a Gaussian is Gaussian. Doing linear things to Gaussians gives you Gaussians. They're a closed family under those kinds of transformations. And that's really nice because when you conditionalize, what you're doing is slicing. And when you marginalize, you're integrating. So the operations that we tend to do to probability distributions, when applied to Gaussians, often leave you with Gaussians. Gaussians are, and it allows us to have this whole system for doing calculations that as long as we stick to those basic operations, Gaussians, everything stays Gaussian. This is just another example of that. We have a Gaussian noise and we have Gaussian prior. We put these things together to get a map estimate. The posterior is Gaussian. And once the posterior is Gaussian, all we have to do is to get the map estimate is basically complete the squares. So here's a slide explaining that. I'll put all these slides will go online. I didn't put them on because I was actually trying to fix some notation and adjust some things. But I think I'm now completely done. We'll put these online so you can actually refer to this. And hopefully there are no more errors or notational problems with the math. Okay, so let's walk through this. This should look familiar because you've seen things that are related to this. This is a slightly different version, but it's many of the same ideas. Okay, so I have a measurement y, which is equal to the true thing, x plus noise, and we'll use mnemonics here. Noise is n, x is the thing I want, y is the thing I'm going to measure. X is, this thing means is distributed as a normal distribution. You've seen this notation also before. This means it's Gaussian. Okay? It's Gaussian, and these are the two parameters. It has mean ux, and it has standard deviation sigma x. Okay? And that's the prior, right? This is the distribution of x. Before I make any measurements, it has a distribution which has this mean and this standard deviation. The noise is also Gaussian. That's what this means. And it has typically noise we assume is zero mean, so it has a mean of 0, and it has a standard deviation, not a variance, a standard deviation of sigma n. Okay? So those are that's the description of our problem. And now, to do a map estimate, we have to write down the posterior. What is the posterior? Well, the likelihood is p of y given x. X is the thing we want. Sometimes we write theta for the thing we want. It's x on this slide. So p of y given x is the likelihood. And what we want to write is the posterior. That's p of x given y. What is the distribution of possible x's that could have led to my data? Y. Y is my measurement. Okay? So that's p of x given y, underlined with red here because I'm going to show you what it looks like in just a second. Color-coded. So here's p of x given y, and that's proportional to, I didn't write equals here. I'm going to use Bayes' rule, but I'm not going to bother with the normalizing thing in the denominator. I said that last time, so let's just write it. P of x given y is p of y given x, the other way around, right? That's the likelihood, multiplied by the prior, and normally Bayes' rule would require us to divide this by p of y, but I'm leaving that out. Why am I leaving out p of y? Because I care about this as a distribution over x, and I'm going to optimize or maximize this over x. And the value of y is, well, that's my measurement, right? And I'm going to assume that's fixed and known. I made a measurement. Here it is. I have a number. That's y. That's fixed. And I now have a distribution over the possible x's that could explain that y. So I want to optimize or maximize this over x, assuming that y is fixed. So P of y, the probability of making this measurement, is a number, but it's a fixed number, because y is known. And so I don't really care about it. It's just going to divide this whole thing. It's just a scale factor. And when I go to optimize this, that scale factor is not going to make any difference. Okay? So this is proportional to this. And now I write out the two Gaussians, because this is Gaussian and this is Gaussian. That's what I told you up at the top. Okay? So P of y given x, what is the distribution? If I know x, if x is a known value, what is the distribution of y? Well, it's the sum of a constant, a known value, plus this n, which is a random variable. That's the noise. So the noise has a Gaussian distribution, and it's centered at 0. If I add this constant to it, what I get is a new distribution, which is the same Gaussian distribution, but shifted over to be centered around x, right? X is just a number. So if I started out with noise that was centered at 0, and I add 10 to it, I get noise that's centered around 10. I mean, this is kind of an almost trivial statement, right? So this distribution, P of y given x, is just the noise distribution, but shifted to be centered around not 0, but around x. So it looks like this. We have e to the minus, there's a 1/2 there. There's a 1 over sigma n squared, that's the variance of the noise. And then there's x minus y squared, because the point is, or you could write y minus x squared, it doesn't matter, right? We're squaring it, so it doesn't matter which order you put them, x minus y, y minus x. It's the y, the variable that is the random variable, centered on x, right? So this is a Gaussian with a mean of x and a variance of sigma n squared. Okay, so that's this piece. Now we have another one. This is the prior, and it is just explicitly, it's P of x, which is just the prior. P of x is, again, e to the minus 1/2. We have a 1 over sigma x squared, that's the variance of the prior, and x minus mu x, right? So now I have the product of the two exponentials. I add the two exponents, I get this. So what's happening here? Well, I've separated out the x squared term, right? So the x squared term is I'm going to get 1 from here and 1 from here. And if I gather them up, here's the x squared term. It has in front of it a 1 over sigma n squared and also a 1 over sigma x squared. There's 1 from here and 1 from here. That they combine like this. And then I'm going to also take the linear term in x. What does that look like? Well, there's one that will come from here. It's going to look like there's a minus 2xy that comes out of that squared thing. A minus 2xy, but it's also times 1 over sigma n squared. So, and then over here, I'll get a minus 2x times mu x and a 1 over sigma x squared. And so if I combine those terms, the two linear terms, I have a minus 2 out in front. And then I have y over sigma n squared, that's from here, and mu x over sigma x squared, that's from here, and those two things are both multiplied by x. So I've just gathered up the linear terms and the squared, the linear terms at x and the squared terms at x. And I didn't write down there's one more set of things. Those are the non-x terms, things that don't depend on x, and I didn't even write them. I wrote ... Because this thing, in the end, is supposed to be a distribution over x. It is a distribution over x, and in fact, it's a Gaussian distribution over x because it's an exponential with a quadratic function of x. Here's an x squared, here's a single x, and then the last term won't have any x's. So this is quadratic in x, it is a Gaussian in x. And this last thing, because it's just constants, things that don't depend on x, is basically just part of normalization. Right? This is an exponential of a sum of three things. The last thing, that exponent of that thing, we can factor it out, and it's just like a multiplicative factor that doesn't depend on x. So the thing that does the real work here, that decides what is the distribution of x, are really these two terms. And then we do, as Mike walked you through last time, we complete the square. And when you complete the square, you say, well, gee, there's this thing that's multiplying the x squared term. That, in the end, is going to be the inverse variance of the new Gaussian, the Gaussian that's describing P of x given y. And so we just read it off. Sigma squared, this is going to be the, I didn't write any subscripts because they're going to drive us all crazy, but this is the variance of the conditional distribution, the posterior. Okay? The variance of the posterior is just 1 over this thing, because this thing is the thing that multiplies the x squared term. right? So 1 over that thing. It's really messy looking, right? It's 1 over, and then 1 over, and then 1 over. There's all these 1 overs. And I think Mike mentioned to you last time, if you express this in terms of precision, the precision is the inverse of variance. It kind of makes sense, right? Things that are more precise have smaller variance. Precision is the opposite of variance. So if you express these in terms of precision, then it's very easy. You say that the new precision, which is 1 over sigma squared, is equal to the sum of the old precisions, these two precisions, the prior precision and the measurement noise precision. Okay, so this is kind of interesting. It's written like this. It's a little bit hard to parse, but if you express it in terms of precisions, the statement is very simple. It just says the precisions add. The precision, when you combine these two distributions, the result is, the new precision is just the sum of the precisions of the two things that you've combined. Precision, the variance doesn't add, the precision adds. Well, when did we see, now you're probably swimming a little bit, like, wait a second, didn't we see a situation where variance adds? When does variance add? Under what conditions? How do I combine random variables so that their variances add? Yeah, so if I have two random variables, and I add them together, I have x and y. No, I better not use x and y, because it'll mess us up with this slide. I have a and b. They're two random variables, and they're independent. And I add them together. I compute a new thing, c equals a plus b. And I want to know, what is the variance of c? And a and b are independent. And the variance of c is just the variance of a plus the variance of b. The variances add. Here we have something that's very different. We are not adding together two random variables. We're doing something a little different. And here it's the precisions that are adding. We're using Bayes' rule to invert this and compute a posterior. And now the precisions add, not the variances. The inverse variances add. Okay? All right. So now let's write the rest of this. The rest of this is completing the square. You take the coefficient that's in front of the x term, pulling the minus 2 out, because that's there in both of these. There's a minus 2 that comes from both of these because when you square the difference, you get a minus 2 times the cross term, right? You take the thing that's multiplying the x, that's this thing in the parentheses, and that is the mean. That's the thing that you have to subtract off of x and square in order to get this expression. So completing the square, you can just read off the inverse variance off of this term and the mean off of this term. So I'm going to write down the mean is this thing, y over sigma n squared plus mu x over sigma x squared. That's just this parenthesized thing. It's this thing, but now I have to actually divide it by the inverse variance, which is this. So it's this thing divided by this. Again, this looks kind of messy. Like there's all these quotients everywhere. It's a quotient with quotients in it, just like the variance was, right? The denominator in particular is like, oh geez, really? I have to divide by something that's got 1 over this and 1 over that? Once again, if you write this in terms of precisions here, let's just write it on the board. If I write it in terms of precisions, I'll call them p, which is a little bit of a problem notationally because we use p for probability, but I'll just write p anyway for precision. The first equation becomes that the new precision is just, I guess it's Pn and Px, right? It's Pn squared plus Px squared. The precisions add, and the new mean, the mean of the posterior is, let's see. How do we write that? It's the precision times y, so it's Pn squared times y plus Px squared times mu x divided by Pn squared plus Px squared. I just realized I'm writing all these squares, but usually when we talk about precision, we talk about it as the inverse of variance. So we don't need the squares. Normally we would just let P equal the inverse of the variance, not the inverse of the standard deviation. So it's just about how you define it. Okay? But so it's easier to write without the squares. So erase all the squares. We're going to define Pn. I'll write a triple equal sign. That means defined as 1 over sigma n squared, and Px equals 1 over sigma x squared. Okay? And then I can write this. And these are easier to parse. Okay? So what's the point? The precisions add. The new precision is the sum of the old precisions. And here, now let's parse this. This one's also easier to parse. What is this? I take y and x. What are y and x? Y is the y is my measurement, the thing I just measured. Mu x is the mean of the prior. Okay, so I take those two values, and now what I'm going to do to those is I'm going to multiply them by these two numbers, Pn and Px, and then divide by the sum of the Pn and Px. Or I could write this as, it might be easier to sort of see what it is. Let's write it this way, Pn over Pn plus Px times y plus Px over Pn plus Px times mu x. So this says that the new mean, the mean of the posterior, is, well, it's a sum of the old means. Here, think of these as the old means. This is the measurement, and this is the mean of the posterior. So I take these two things, and I take a weighted combination of them. And what are the weights? Right? I take a little bit of this one and a little bit of this one. What weights do I use? Well, these are the two weights. And these two weights are just two numbers, and these numbers are normalized so that they sum to 1. Right? So if this one is, 0.3, and this one is 0.6, I normalize them out by 0.9, and it's 1/3 and 2/3. Right? So these numbers, or if this one is 1 and this one is 4, when I normalize them out, I divide by 5. This one becomes 20%, and this one's 80%. What I'm doing is taking a weighted average. This is a weighted average of these two things, the y and the mu x. And the weighting is precision. It's precision weighted. It's a precision weighted average. Okay, so I'm going to put the phrase here: precision weighted average. It's an average of the two things, an average because I'm going to add them up with weights where the weights add to 1. Right? But it's not just a flat average, it's a weighted average, and the weighting is according to the precisions. The more precise of the two things gets a higher weight. Makes a lot of sense, right? I'm just saying if the measurement is really precise, then weight that really heavily. If the measurement is really bad, a lot of noise, and the prior is pretty precise, then weight that heavily. Combine these two things according to their precision. That's the basic rule. It's very intuitive, it's very sensible. It's kind of messy when you write this out, but actually it's really easy to understand what it is. It's the precisions add, and this is a precision weighted average. That's it. That's all it is. Okay. And here's a picture, just so you know what these distributions are looking like. So the blue one is the prior. In this case, it's centered at, I guess, something like -1. And it's kind of wide, but not really wide. And then the measurement comes in, and the measurement is at +1, and is a little bit narrower. That's the green. That's the likelihood function. The green is the likelihood. Okay? And now I take the product of the green and the blue, and it's kind of hard to imagine visually that if I multiply this blue function times this green function, what comes out is another Gaussian. It doesn't look like it. You might think that it's going to come out looking like some weird function, some weird lumpy thing. It's not, because, well, we just proved it, basically. If I multiply two Gaussians, I get another exponential with a quadratic in the numerator. It's another Gaussian. So out of the product of the blue and the green comes the red, another Gaussian. And this Gaussian is always narrower than the other two. Why? Because the precisions add. And the precision is the inverse of the width, or the squared width. So if I add two of these together, the end result is always bigger. These are positive numbers, of course, because the inverse variances, they have to be positive. If I add two of these things together, the resulting precision is bigger than either of the two individual precisions, because it's the sum of the two and they're positive. And so I get a bigger precision, which means I get a smaller variance than either of the two variances that I started with. So the red curve is always narrower than both the green and the blue curves. Okay? So, and the mean is a compromise. It's somewhere in between the means, or if you like, the peaks. These are Gaussians, so their mean is their peak. The mean of the red curve must lie in between the mean of these two guys, and it will be closer to the one that's more precise, which is exactly what you can see here, right? That's because it's a precision-weighted average, right? So it's going to be somewhere in between the two, and depending on which one is more precise, it'll lean toward that one. If one of these is really narrow, the green one's narrower than the blue one, then you lean that way. Okay? So, like I said, everything is actually very intuitive. The math, a little bit messy writing this out, going through completing the square, but in the end, the answer is actually very intuitive, very sensible. Okay. Now, what if I make another measurement? What happens? So, right, we talked about this sequential, the idea that you can write this out sequentially, right? So I make one measurement, and I plug it in, I combine it with my prior, and I get this, right? Now I make another measurement. And the assumption is always that the next measurement will come in, let's say, with the same noise, the same amount of noise, but it will be a new sample of noise, and it will be independent from the previous measurement. So, you know, one measurement comes out a little high, the next one comes out a little low, or not. It's a sample, another sample from the same distribution. So the noise, I'll grab another sample out of this noise distribution, but it won't get the same value. It'll be just an independent sample. Okay? And now, what happens? I want to do math estimation, and I have two measurements. How do I do that? Well, I mean, first let's just write down what is the posterior. I just want to make sure everybody sees where this comes from. Once you see it, it's sort of obvious, but it might be mysterious if you haven't gone through it, so let's just write it, okay? So I first write down, what do I want? I want P of X given, now I'm going to make two measurements. So I've got, let's call it Y1 and Y2. Of course, we could make a vector of Y's. Has the two measurements in it, but let's just call it Y1 and Y2. We'll write it out explicitly because there's only two of them. And we use Bayes' rule to write that. That's just P of Y1 and Y2 given X times P of X, and of course, well, we'll be complete about it. There's a denominator that looks like that. And of course, the same statement holds that I made before. Denominator is there. If I want to write this strictly as an equality and really express this as Bayes' rule, that's it. The fact that there's two variables, y1 and y2, doesn't matter for Bayes' rule. Think about that as a vector that contains the two-component vector, right? A length 2 vector that has these two numbers in it. Then this is just P of X given that vector y is equal to the P of the vector y given X times P of X divided by P of y. Okay, so this is just Bayes' rule. And now we have one more thing to do. Well, so if I'm interested in maximizing this over X, then once again, the denominator is not going to matter. It's just that it doesn't have any X's in it. So when I go to optimize this, if I try to, for example, differentiate it and set it equal to 0, the denominator is just a scale factor. It's not going to make any difference. It's just a number. So again, that's why on the slide we kind of ignored it, and we could ignore it again here. What about the numerator? Well, now we have one more thing. So this equality is here because of Bayes' rule. And this equality that I'm about to write, we'll write it first. And I have one more thing I want to do. There's a probability over two variables here conditioned on X, right? So I'm looking, what's the distribution of the Y's given X? Well, both of them are going to be Gaussian, centered at X, with a width equal to the standard deviation of the noise. Because they both arise the same way this one did, right? So this P of Y given X, it's this Gaussian. It's a noise distribution, but shifted to be around X, right? Y is X plus N. We're writing down the distribution of Y conditioned on X as if we know X. So this is a Gaussian, each of these is a Gaussian distribution centered on X with variance sigma n squared. And they're independent. So the joint distribution of these two variables, the probability of this one and this one conditioned on X, is just the product of their two individual distributions because they're independent. So we write P of 1 y1 given X, P of y2 given X, and P of X. And this equality is because of independent measurements. Right? That the noise in the two measurements is independent. They're independent samples. Okay? So now, oh, and I guess if we're keeping this, we can keep the denominators here, even though we know we don't need it. Give y1, give y2. All right. So we just took this and rewrote it like this. And sometimes people get confused when they look at these things because they think, well, wait a second, why is, don't I need another, like if I think about Bayes' rule, I have this thing times P of y2 given X times P of X, that's one Bayes' rule that'll give me kind of a joint distribution of y2 and X. And don't I need another P of X to go with this one? And the answer is no. This is what you need. You need one P of X, that's the prior, and then you need each of your likelihoods. 1, 2, and if you made another measurement, there would be another one. If you made another, it keeps telescoping out. So this is why you can do this sort of sequential updating when you think about the map and posteriors. The posterior is just a product of the prior. That's kind of, think of that as your anchor. That's before you made any measurements. There's no y's, you just have a prior, that's P of X. Now you make your first measurement, you get this term. You multiply that guy by this. Now you make another measurement, you put that one in. If I make a third measurement, I'm going to put another one in. Don't add, you multiply another one. Right? You have each of your measurements get slapped on here in this big long product. If you're doing it again as log of the posterior, then it's the sum of the logs of each of these terms. Question?
So for example, if y is your spike count from multiple neurons,
yes.
and you think that the neurons are dependent on each other, you can't use this way.
Okay, so that's a slightly different configuration, but let's do that. So here, I'm assuming that these y's are measurements of the same thing. The thing that they're measurements of are x. Okay, so there's this true thing x, which is what I want to know, and I'm making multiple measurements of that thing. And each measurement that I make gets combined into this product like what's shown on the board. What you just asked about is, I have two neurons, and I'm going to make measurements of those two neurons. Do I now just multiply out the probability for those two neurons? So you have to think for a second and realize that the two neurons, the thing you're trying to estimate, let's say, is the rate of the two neurons. So it's a lambda in a Poisson process, but there's two of them. There's not one lambda, there's two lambdas. And the two neurons have different firing rates, or they at least could have different firing rates. So you actually don't want to combine those in this way, because this is assuming that what I'm after, the x that I'm after, is the same x. So this, I mean, a lot of experimental manipulations and the way we build experiments and make measurements is about sort of separating out things that are measurements of the same thing versus measurements of different things. And you have to be really careful when you go to combine these things. If you have multiple neurons, you're not generally going to assume that they are having the same firing rate. Okay, so you would not do this for that case. There, what you really want to do is you want to think of, if you like, the x now becomes a vector. It has two components in it. They're the two things you're trying to estimate. Think of those as lambda 1 and lambda 2, the rates of the two neurons. And now you can talk about what measurements are you making. Maybe you're making a joint measurement of the spike count of the two things. And now your measurement model, this is a measurement model. This is a description of what I think the relationship is between my measurement, that's y, and the true thing, which is x. So whenever you do any kind of estimation, the first thing you need to do is to write down what do I believe my measurement model is. That's what this is. Okay? So for the neurons, you'd say, okay, there's 2 lambdas, so I have a vector that takes the place of x here. And now I'm going to make a measurement with, I don't know, 2 electrodes. That maybe takes the place of y. And that what I'm going to measure is not the actual rates, the lambdas, but I'm going to measure spike counts from these 2 neurons. And then you might ask yourself, well, do I have a prior on these 2 neurons? Do I believe that for example, the distribution of rates ahead of time, what does that look like? It's probably not Gaussian. It's got to be positive, so you probably want to choose a prior that's a positive value distribution, maybe an exponential over. And then you have to ask yourself, do I believe that they are correlated ahead of time? Do I know anything about these neurons? So there's a whole bunch of things that go into formulating the measurement model and formulating also the prior. If you're going to do a math estimate, you're going to need a prior. But you would not, you can't just bundle everything together the way I'm bundling things together here. It's really just about being careful to define what is the thing I'm trying to estimate and how do the measurements relate to that.
And it's worth pointing out that even in the model that we're currently working with above Eero's hands, there's the concept of independence and the concept of conditional independence.
Yeah,
so if you didn't know X, and you're not assuming anything about X, you don't know what the state of the world is, and you collect 2 measurements, Y1 and Y2, they're not independent. Because if X is big, they'll both be big. And if X is small, they'll both be small.
This is on the next slide.
That's on the next slide.
Yeah.
Oh, I didn't remember that.
It's okay.
But the point is, the reason we're allowed to act like they're independent here is we're not putting P of Y1, Y2 equals P of Y1 times P of Y2.
Right.
What we're writing is, if we know X, or assume a fixed value of X, then at that point, these are just random draws from the distribution centered on X. So
Yeah.
they become independent once you know X. They're not independent if you don't know X. So they are conditionally independent, but they're not just simply independent.
Mike is absolutely right, and I should have said it that way, so thank you for interjecting that. Conditionally independent measurements, right? It's not, the way we wrote down independence and defined independence on random variables was, right, we said the 2 random variables are independent if and only if we can rewrite their joint probability as a product of their individual probabilities. That's correct. This is just the same statement, but these are now conditional probabilities, as Mike was just saying, right? So it's this distribution. It's the distribution of the y's conditioned on x, in which these 2 things are independent. And I can rewrite this as a product of the 2 individual conditional distributions, which is what I did. Okay. On the next slide, we're going to go through an example where that is not true, and we'll walk through why. Okay. So we have, now we have a posterior if we make 2 measurements. And well, what happens, let's go back to the slide. Right now we've got a Gaussian. We started with a Gaussian. This was Gaussian. We made 1 measurement. That's what's on the slide. And we computed the posterior with that 1 measurement in place. And we got a new Gaussian. The posterior is a new Gaussian, such that its precision is the sum of the original precisions, and its mean is the precision-weighted combination of the original 2 measurements. They're not measurements. One is the prior and one is the measurement. Okay, so we're going to do the precision-weighted combination of the 2. Now, what happens next when we add another measurement? Okay, we have to now combine 3 of these things. So you might think, oh my God, are you serious? The next slide is going to be a product of 3 of these exponentials, each one of which has a quadratic term. Each one of this has to be expanded out. Each one of these have to be gathered together and factorized, and we have to complete the square of this new, even bigger thing, because now it's got 3 of them. Nicely enough, you can kind of see that the rules for doing this, are going to be a continuation of the simple rules that we've already got. Okay? So what's going to happen when you go and you write out those 3 terms with 3 exponentials and you splat them together like this is you'll get here, instead of 1 over sigma x squared plus 1 over sigma n squared, you're going to have another one, but it's another 1 over sigma n squared. Comes from the other measurement, right? You already had one from the prior, one from the measurement. When you put another term in here, you'll get another one, which is another one. It's another measurement. It'll be a 1 over sigma n squared will show up again. So you'll have 2 of those. And over here, same thing, except now it'll be just a slight subtlety. It'll be y1 divided by sigma n squared. That's the first measurement. But then you'll have another one, which is y2 divided by sigma n squared, and that'll be added into this term. And when you think through how does that play out down here, the answer will be, oh, well, the new precision will be what used to be just the sum of the precisions. I erased it, it's on the board in terms of precisions. It was the sum of the precisions of the prior and the noise. Now it'll be the sum of the precisions from the prior and the noise again, because there's another noise term. So it's still the sum of the precisions. It's just that it's now the sum of all 3 precisions. And if I make 10 measurements, it'll be the sum of the 10 measurement precisions, i.e. I'll get 10 times the precision of the measurements, and then there'll still be the prior precision. So it'll be those 10 plus the prior. So the precisions will still add, which sort of explains why as you roll along and you keep adding measurements, the precision keeps going up. You keep adding 1 over sigma n squared. That's the precision of the noise. You keep adding those precisions. And by the way, you can see now the convergence, right? If you didn't have the prior, what would this do? On each step, I'm adding another copy of this precision. So the total precision after n of these measurements will be n times the precision of the noise. What is the variance doing? It's going as 1 over n times the noise variance. Oh, that's nice. The variance of our estimator is going as sigma squared divided by n. Oh, it's right there. Because the precisions are adding, they go up as n, then the variance goes as 1 over n. Oh, so that's just, we already knew that. That's the standard error of the mean. That's the thing that we learned a long time ago. So everything is consistent. Just add the precisions and it will march along. It'll grow linearly as you make more measurements. It's the only thing that's different now is just that we don't start off at 0. We start off at the precision of the prior, right? There's this 1 over sigma x squared term. We always initialize with that instead of starting with 0, and then we just add precisions for each of the measurements one at a time, however measurements we make. And eventually, if you got a lot of measurements, if n is really big, this thing basically looks the same as if I just added up all the measurement precisions, because the prior precision is just one little tiny term in the midst of that giant collection of measurement precisions, right? So that in the end, the measurement precisions are going to dominate this, but not in the beginning when you only have a few measurements. It's likely that the prior precision has a big effect. Okay, so that's that term, and what happens here? Well, you know, it's kind of the same thing. This is still going to be a weighted sum of these guys. It'll now be a weighted sum of this mu x, and each of the y's, each of the measurements, in our case on the board, it's 2 measurements, so it will be y1 and y2, each weighted by sigma n squared, and then divided by the sum of the 1 over sigma x squared and the 1 over sigma n squared. So once again, it's going to be a weighted average, precision weighted average. So the rule that I gave you for how this pans out, that this thing is just the sum of the precisions and this is a precision weighted average, that's still going to hold. No matter how many measurements you make, that's what this is going to look like. You get a precision weighted average and you get the sum of the precisions here. Okay? So the rule just telescopes out in a very simple and natural way. Once you understand that, you barely have to think about it. It's actually pretty obvious and very intuitive. Okay.
So
Questions?
Yeah.
Yeah.
It's a Gaussian centered on X with variance of the noise.
Correct.
With the noise. Well, why the variance is the noise?
Right, so here's the noise by itself, right? This is, the width here is, you know, determined by sigma n, right? And it's centered at 0, right? That's P of n, right? Now if I wanted to know P of y given x, which is where y is x plus n, but x is, in this, x is known, right? So this is assuming that I know x. If x is out here, what is the distribution of the noise plus x? Well, it's just this distribution, but translated over, right? draw samples of this, they're going to come out of this distribution, right? But if I draw samples of y, assuming that I know x, what am I going to get? I don't get samples from here. I get samples of whatever the sample of the noise is plus x. So I just get, it's like drawing samples from this. Okay? So the distribution of y is going to be what's written up there. Right? It's Gaussian, centered at x, but with a width of sigma n. Okay. And that's what's on the slide. Okay, so that's it for map with Gaussians. That's really all it comes down to, and that's what I wanted to tell you, right? So the map estimate is a weighted average. It's actually a precision-weighted average of the prior mean and measurement. Yeah?
So that question's similar to the last question.
Go ahead.
On the last slide?
Yep.
Based on based on what you just said, why is P of y given x drawn not the mean as, like, why is the mean of the green one not the same as the mean of the blue one?
Because the blue one is the prior. The mean of the blue one is mu x. The distribution of x with no measurements, just x by itself, we're imagining that it's drawn from some distribution which is Gaussian. It has its own width, that's sigma x, and it has its own mean, that's mu x. Okay? So that one has, it's this distribution. Okay? So x minus mu x, this is the mean, and divided by sigma x squared. So this is a Gaussian that has this mean and this variance. Okay? So this is a different distribution than this one. When you start adding more measurements, each one of those is going to look like this one. You'll have y1, y2, y3, y4, but they'll all have the same width. The sigma n is the amount of noise, the variance of the noise. So we're assuming that all measurements have the same amount of noise in them. Each sample is a different noise sample drawn from this distribution, but it's always the same variance. Okay. That's the assumption of this setup. Did that explain it?
Yeah.
Go ahead.
The green one is centered on y.
The green one is centered on y. That's correct. But maybe we should label these. That this is assuming this measurement y is equal to, let's say, 1. I think it's about 1 here, and it's assuming mu x is about around -1. Okay. And then the result is that the posterior is narrower than either of those and has a mean, it's centered somewhere in between them, right? And that's just because of what I told you here. The precision goes up, and the mean is a precision-weighted average of the two original means. Go
So
ahead.
the green one centered on y, which means this one centered on y?
No, that's different. That's this is here I'm describing p of x given y, right?
It's the red one.
Here I was describing p of y given x, which is not any of these.
It's the green one.
It's the green
Sorry,
one.
that's the green one. Yes, thank you. Yes,
But
which
the
is
green
centered
one,
at y.
the green one is drawn as a function of x. This
Correct.
is drawn as a function of y.
Yeah, so this is the confusing thing about likelihoods versus. So is this axis x or y? If we're thinking about estimation, we want to think about this as axis as x, and we want to think about this as a likelihood. This is this strange thing of thinking of this as a function of x, even though it's actually really a function of y. So here, you're writing this as a Gaussian around y. I know this is confusing. This is the measurement description. What I wrote here and said is correct. What is written here is also correct. It just requires you to flip everything around a little bit and think of this as a likelihood. I said this before in the abstract when we introduced this. I said there's something very strange about the definition of a likelihood function. Normally, when you write a conditional probability, you think of this as a function of this first variable, that's the random variable, and this x is just a constant. And something very strange about a likelihood function is you do the opposite. You assume that the y is a known measurement, it's fixed, and it's the x that you're looking at as a variable. And this is plotted as a function of x. The green thing is a likelihood. So it's kind of backwards. You can still do it. It's just an equation. Here it is. This is an equation. And notice in this equation that this is actually the key point, and maybe this will help you. I'm sorry this is confusing, but that's actually because it's been confusing for 150 years. Not because it's confusing right now. I'm trying to make it a little less confusing, although I may not be succeeding. Look at this piece of equation, okay? The probability of y given x, which is written right here, if I'm thinking about this as a distribution over y, x is known, and y is the random variable, and I could plot this as a function of y. But notice that it's symmetric in x and y. The way x and y enter this function, it's the same. It doesn't, I could rewrite this as y minus x. It doesn't change anything, right? Because I'm squaring it. So flipping it to write it as y minus x doesn't change anything. And that means this function is the same if I write it as a function of y, and I draw a plot of that, and next to that I draw a plot of this thing as a function of x. I get the same function. It looks the same. X and y are entering symmetrically. So if I hold one fixed and plot it as a function of the other, it's the same function if I hold the other one fixed, okay? And that's why when I wrote this, I actually was drawing it as a function of y. This x is a fixed number, and this axis here is y. But what's drawn on the slide is in little tiny font down here. We're going to make that bigger. There's an x. This is a function of x because I'm thinking about the posterior, which is, I'm going to think of that as a function of x. And each of these is drawn as a function of x, including the green one, even though the green one is sort of a function of y. But we get around
y is known and x is.
Right. So there's nothing wrong. The math is just what it is. It's the interpretation that's a little bit weird. That's because a likelihood is a weird thing. A likelihood is reading a probability distribution kind of backwards, right? Holding the wrong thing fixed and letting the other one vary. You can do it mathematically. There it is. Here's the function. Hold x fixed and let y vary, or hold y fixed and let x vary. You can do either one, right? Think of this as a two-dimensional function of x and y, and what we're doing is you can slice it this way, or you can slice it this way. It's the same function. It's a perfectly legitimate thing to do. And that's really all this is about. Right? So when they're plotted here, they're expressed as functions of x. Everything's a function of x. Okay. I hope that helped. I'm seeing a lot of puzzled looks. I don't know how to make it any clearer. It is a weird thing. Okay, let's do the next thing, all right? This one's kind of fun because it goes back to something incredibly basic and something that is confused constantly. And people make this mistake all the time. You see newspaper headlines that make this mistake. You see people getting confused about it. And here is a Bayesian explanation of this confusion and why it arises, okay? So I'm going to imagine exactly what Mike said a moment ago. Let's imagine, we're going to imagine I have two measurements of the same variable. So the way, I probably should have used the same notation, but it's a little bit different. So I have z is a variable that's unknown, and z is normal with some distribution sigma z. And I'm going to make two measurements, x1 and x2. And these measurements are, x1 is z plus n1, and x2 is z plus n2. And I'm going to assume these two noise amounts, just like on the previous slide. These are noise samples, and they're drawn from the same distribution, but they're independent. Right? So I'm making two measurements of the same thing, but it's just what I was saying on the board. I imagine I've got two measurements of y's here instead of x's. And there's, and the thing that I'm measuring are measurements of z, okay? So the joint measurement distribution of the x's is normal, and it has a mean of 0, because here I'm going to assume that the prior has a 0 mean. There's no mu z here, it's 0. So this is normal with a mean of 0. Why is that? Well, the mean of each of these components, each of these x's, each of these x's is the sum of two variables, so the mean of the x is the sum of the means, because, right, expectation is linear, so I'm going to take the expected value of this and the expected value of this. The expected value of c is 0 by assertion, and the expected value of n is 0 by assertion, so the expected value of x is 0, and that's true for both x's. Okay, so these things are 0, and their joint distribution, though, and here's what Mike was referring to a moment ago, if they're not independent. What does their joint distribution look like? Well, think in this sense. Well, actually, you can see it in the plot, since I didn't animate this. It's all here. These points are samples of x1 and x2, and you can think of it as like z lies along this diagonal line. So you pick a z. We're not going to assume z is fixed now. We're going to actually imagine that we're going to sample over different z's, and for each z, we will have two measurements, x1 and x2. So these points represent different measurements that are made. They're made for different z's, okay? And each of these points is made for different z's. And what happens is the z is running along here, and it's Gaussian distributed, and then for each of those z's, you get measurements which are splattered in both directions by the noise, right? That's what the n1 and the n2 are doing. Okay? And you end up with this splatter. And now, it's not hard to work out that this joint distribution is also Gaussian. These things are both Gaussian. We're adding together Gaussian random variables, and the sum of two Gaussian random variables is Gaussian. Because the joint distribution is like the convolution of the two things, right? And so that, and a convolution of two Gaussians is Gaussian, so that everything stays Gaussian. Okay, so I end up with a Gaussian distribution, and now what I'm going to do is describe what's that Gaussian distribution of x look like. And what does it look like? Well, it's got, you can calculate it based on where does it come from. So the x's are just the sum of these two things. What's the mean? We already did this. The mean of the x's are both 0. So the mean of the joint distribution is 0. That's right here. What about the variance? It's not a variance anymore. It's a covariance because this is two-dimensional. Okay. So you can think through those terms one at a time. What's the variance of the x1 term? Okay. What's the variance of x1? Well, it's a sum of two random variables, and they're independent. So the variance of a sum of two random variables is the sum of their variances if they're independent. So the variance of this guy is, let's write it down on the board so we can keep track. We're going to make a covariance matrix. We can call this CX, covariance of X. And in the upper left-hand corner is going to be sigma, think of this as sigma squared 1, 1. It's the variance of x1, the x1 variable, okay? And what is that? Well, it's got to be the variance of z plus, let me write it down. The variance of x1 is equal to the variance of z plus the variance of n1. And what are those? Well, that's sigma z squared plus sigma n squared. And this is true because these are independent random variables, right? Z and n1 are independent, and therefore their variances add. Okay. So the new variance, so what goes up here is sigma z squared plus sigma n squared, right? That's in the upper left-hand corner because it's the variance of this guy. What goes in the lower right-hand corner, that's easy. That's going to be the variance of x2, and that looks the same, right? x2 is z plus n2, but it's the same rules. They're independent, so the variance is add. So down here, I also get sigma z squared plus sigma n squared. No difference. Now, there's one more thing I have to figure out, which is what's the variance, or the covariance, let's call it, of x1 and x2. So how do you compute that? You take x1 times x2. Technically, you would have to subtract off each of their means, but their means are 0. So it's just the product of x1 and x2, and what's the expected value of that? So how do I get that? Well, let's write it out. It's expected value of the product of x1 and x2, so it's going to be z plus n1 times z plus n2. I'm taking the product of those two things, right? I have to actually take the product of these two sums. So let's write those terms out. It's the expected value of, I get a z squared, I get an n1 plus n2 times z, and then I get an n1 times n2, right? So what is that in the end? The expected value of z squared, well, that's sigma z squared, right? That's the variance, because it's a zero mean variable, so it's sigma z squared. What's the expected value of, let's see, n1 times n2 times z, plus n2 times z? This is n1. Well, n1 plus n2, that's another random variable, the sum of the two. And I'm taking that thing times z. But these things, these are uncorrelated. They're independent, the n's and the z. So if I take the expected value of this product, I get 0. And the same thing for the product of the n1 and the n2. The expected value of that product is also 0 because these guys are independent. So in the end, all I get is sigma z squared in this corner.
Because they're independent and because their individual expected values are all
Are
0.
0, right? Everything is 0 mean here. It keeps everything. When you take products of random variables, if they're independent, the product of the expected value of the product is the product of their means, actually. But if their means are 0, then the expected value of the product is 0. So I made the problem a little bit simpler by putting all those 0 means in. It makes it easier to see what's going on. Okay? So the covariance matrix that we end up with looks like this. On the diagonals, we have sigma z squared plus sigma n squared. And on the off diagonals, we have sigma z squared alone, which is, of course, smaller than sigma z squared plus sigma n squared. Right? By symmetry, you can see that what this is going to be is it's a Gaussian distribution, we already said that, and it's going to be kind of along the diagonal. It's going to be like tilted at 45 degrees. Another way of saying it is, if I did total least squares regression on this thing, and I asked, where is the direction in this data cloud that has the biggest variance? Well, this ellipse kind of captures the variance in all these directions, and the biggest variance is in this direction, the 1, 1 direction, and the smallest variance is in this direction, which is the 1, minus 1 direction. Can we convince ourselves that those are actually eigenvectors? We should be able to, right? These should be eigenvectors of the covariance matrix. I'm pulling way back to when we did least squares. The way total least squares works is you take your data and you calculate essentially a covariance matrix, and then you take the eigenvectors of that and they tell you the principal axes of the ellipse that describes the variance in all directions. So the principal axes here should be 1, 1, 45 degrees, right? And 1, minus 1. We can check it. If I take this matrix and I multiply it by what is Cx times the vector 1, 1? Well, we can calculate it, right? This matrix times 1, 1, I get, right? Tip it over and do that Raffetto's thing, right? The sum of these two things is the first component, the sum of these two things is the second component. So I get 2z squared, 2 sigma z squared, thank you, plus sigma n squared. And then on the second one, I again get 2 sigma z squared plus sigma n squared. Oh, cool. So I get out a vector that looks just like the 1, 1 vector, i.e. it has two components that are identical. But they've been rescaled. That's okay. That's what eigenvectors are supposed to do. They don't come out the same. They come out rescaled. So now I know not only that this is an eigenvector, but I know what the eigenvalue is. The eigenvalue is 2 sigma z squared plus sigma n squared. Because if I factored that out here, I would see that the Cx times 1, 1 equals this number, 2 sigma z squared plus sigma n squared, times 1, 1. Okay, I got an eigenvector. Win. Now, what about the other one? Can I show the other one's an eigenvector? 1 minus 1. What does that do? So now it's, when you multiply by this, you get this minus this. So So it's sigma z squared plus sigma n squared minus sigma z squared, so the sigma z squareds go away, and I get sigma n squared here. And what about when I multiply this, I have to do the bottom row. The top row times 1 minus 1 is the difference of these. The bottom row times 1 minus 1 is sigma z squared minus this thing. So again, the sigma z squareds cancel, but now I get minus sigma n squared. Cool. It worked. No mistakes. Look, Ma, no mistakes. It looks like 1 minus 1, except it's multiplied by another number, which is sigma n squared. So now we know what the two eigenvalue vectors are, and we know what the two eigenvalues are. And in this case, those are describing how wide the ellipse is. Well, the square root of those tells us how wide this ellipse is in these two directions. How wide is it? Well, in this direction, it's sigma n. That's the second one. And in the other direction, it's 2 sigma z squared plus sigma n squared. Take the square root of that. So it's much bigger this way. And how much bigger? Well, it depends on what sigma z is. Notice that sigma z dropped to 0, then this thing is now circular. And what does it mean? It means that there's only one z out there in the world. There's no prior over z. Z it just has one value. It's at 0, and what you're looking at is noise. And it's circularly symmetric because the noise is independent Gaussian draws, so it's the same in both directions, and that has a spherical shape, right? The variance is the same in both directions, and it's uncorrelated. Okay, so that's our situation. We have a measurement, the joint measurement, x, the vector, gives us this splatter of things, and we now know fully how this splatter looks. We know that it's Gaussian, we know what its covariance is, we even have a geometric interpretation of its covariance. Okay. Now, pretend you didn't know any of that. Oh, I'm getting the timeout thing.
Yeah.
Okay, fine. Timeout. See you in a few. You weren't running the camera during that? You need to record that. Okay. All right, so now we get to turn things on their head a little bit and point out why something that is you probably have heard about, but we're going to try to explain why this thing happens that people stumble over all the time, including many newspapers, even the New York Times. Okay, least squares regression. We've seen it a lot. Here it is again. So you're trying to compute the minimum over value of x2 minus some beta, that's the slope of the regression line, times x1. And here again, I've assumed the means are subtracted out because everything is centered at 0. And you minimize this over your data. I didn't put in to label for the data, but your x1 and x2, those are going to be for every one of these points, and you have to sum this over all those points, and you minimize that squared error. And we've been through tons of stuff about how to solve these problems, the mechanics of using linear algebra and thinking about how you solve this problem. And you know what the answer is. The answer is, well, depending on how you do it, what we used to do is we would get something that looked like you make a vector of all the x2s, you make a vector of all the x1s, and the beta that optimizes this looks like what? Well, it's the dot product of the x1 and x2 vectors divided by the squared length of the x1 vector. That was the answer. Or if we want to think more statistically, it's the correlation, or the, let's not call it the correlation, bad word. It's the covariance term of the x1 and x2, i.e. it's this guy in the covariance matrix divided by this guy in the covariance matrix. It's the same thing. We actually did that a bunch of lectures ago, right? These things are all interrelated, right? Because it's all about quadratic forms and it's all about vectors and their lengths and their dot products. It goes all the way back to the linear algebra that we did on the second day of class. I told you the whole class is cumulative. I meant it. Everything is, it's all interconnected. We're using the same things, the same manipulations, the same calculations, okay? So now, so this ratio, this thing, beta, the thing that optimizes this, the argmax or argmin of this, if we're doing probabilities, we're usually maximizing. If we're doing negative log likelihoods, we're minimizing. This is going to be minimizing because this is the squared thing, whatever. The argument that minimizes this is the ratio of this guy to this guy, which I've written here. It's sigma z squared
You
divided
also
by the
saw this
sum.
at the beginning of the last class when I corrected the math on what the conditional distribution is and
Yeah.
explained it. Remember, it was P11 over P12.
Yeah, it's the same thing.
Or did I just say that upside down?
P12 over P11.
P12 over P11, which is exactly what
Which is exactly this. Yeah. Oh no, maybe it is the other way because they're precisions. You're talking about precisions.
Yeah.
You have to flip them. Precisions. They're 1 over.
Yeah.
Anyway,
Yeah.
let's not worry about it. You see where this came from. And you've seen it before, right? So now you look at this thing and you say, oh, look at that. It's sigma z squared divided by sigma z squared. Ooh, that's in the top and the bottom. And then there's an n squared also in the bottom. These things are all positive. So this is, what is this number? It's a number between 0 and 1. If sigma z squared is really large, so this is 1,000 and this is like 1, that's the noise of variance 1, then this is 1,000 divided by 1,001, so it's pretty close to 1. And if sigma z squared is really tiny, like it's 1/1000th, then I get something tiny here, something tiny plus 1, then this whole fraction is close to 0. And so sigma z squared decides whether this number is close to 0 or close to 1. And that means it decides whether the slope of the red, this is the regression line, the beta is the slope of this line. The slope of this line is between 0 and 1. Now, isn't it weird that the data are distributed symmetrically, like along this 45-degree line, but the regression is not? And in fact, the total least squares problem would tell you that this is the best, this is the axis that describes the data best, right? We did that. This is an eigenvector, that's the green line. But the regression line, the least squares regression line, is actually like this, and in fact, it's always less. The slope is always less than 1. This number is between 0 and 1, but it's never, unless you really let this sigma n go to 0, this number is not going to be equal to 1. It's going to be like, you can get close to 1 if you make sigma z really big. But it's generally between 0 and 1. So this red line is always sloped like this. Isn't that weird? It seems weird. What it means is that, for example, if you tell me one way to interpret, there's lots of ways to interpret this. We have talked about this, right? We can interpret this as, variance explained. That's the sort of correlation approach. We talked about R squared. We talked about thinking about this, that kind of interpretation. Now we have a sort of different interpretation. I want to think about it in terms of estimation and conditional estimation. So if I ask the question, if you tell me x1, that's the horizontal axis, right? You tell me x1, you make one measurement, you tell me what it is. So let's say it's over here. It's at minus 1, okay? I know x1, I got it in my pocket. Here's the number. Now, what do you think x2 is going to be? I'm going to make a measurement of x2. What do you think it's going to be? On average. You might think to yourself, well, if x1 was -1, I'll bet x2 will also be -1. And why would you think that? You think, well, x1 is some measurement of this thing z, the thing that I care about. And my current concept of what z is that it's -1. That's what I think it is, because that's the measurement that I made. So if you ask me, what do you think your next measurement's going to look like? The obvious thing to answer is, well, I think it'll be about around -1. And that'll be wrong. That'll be incorrect. On average, your next measurement will not be -1. If this measurement is -1, and I go up along this line, and I ask, what do I think the next measurement will be? It's not on the green line. The next measurement, on average, will be here, where this x is. It'll be less than -1, not less. It'll be closer to 0. That's kind of weird. No matter what measurement I make, my best guess for the next measurement is not that it'll be the same as the one I just made. It'll be that it'll be something in between the one I just made and 0. This is just a restatement of all the stuff we've been looking at on the previous slide. After you make a measurement, your best estimate now is not equal to your measurement. It's a compromise between your measurement and the prior. And your best estimate of the next measurement is that same compromise. So this is a very weird thing, because it means, and by the way, this whole plot is symmetric, So if I flipped it around and asked in the other direction, I said, well, what do you think if I instead, I looked forward in the future and I took x2, and I conditioned on that instead of taking a vertical slice, I take a horizontal slice, I tell you what x2 is, and I say, what do you think the next one will be, the x1 was? The answer now will be not this red line, but another red line that's symmetrically on the other side of the green line. So there's nothing special about vertical here, it's just that we've chosen to make x1 the variable that was measured first and that we know, and x2, we're conditioning x2 on that. That's what gives us this red line. If we flip it around and condition the other way, everything is symmetric and it'll go the other way. Okay, so this is a very weird situation when you first encounter it, and it leads to these crazy things that people say, which I'll show you on the next slide. But that this fact, the fact that things, there's a phrase that gets used, regression to the mean, which tells you that when you make measurements, and you condition like this, your subsequent measurements tend to get pulled toward the mean. And it leads, so this is not something special about these data. This is something that happens all the time, and it happens in real-world data sets, and it's basically automatic, but it leads people to do these false things about reasoning when they think about regression. Okay, so here's a quote from Danny Kahneman, which kind of illustrates this better than I can, because it's also kind of funny. Depressed children treated with an energy drink improved significantly over a 3-month period. And he says, I made this newspaper headline up. I just made it up. But I also know that it's true. Like, what? What are you talking about? You made it up, but you know it's true. If you treat a group of depressed children for some time with an energy drink, they will show clinically significant improvement. Why? Because all you're saying is, I have a bunch of children. They have some range of depression. Let's zero center it, and I have some measure of depression. We'll zero center it. So that positive means they're not depressed, they're actually very happy. Negative means they're kind of depressed, and there's everything in between, the whole range. Each child has, let's say, some assigned, maybe it's genetic, perhaps. They have some level of depression, which is fixed, and I make a measurement. That's x1. And then I wait 3 months, and I come back and make another measurement. If I take all the children that are kind of down here on the depressed side of the scale after the first measurement, that's x1, I take all of these and I ask what happens to them 3 months later when I measure them again. The next measurement, that's the regression line again, their next measurements will generally be better. They will go towards 0. They'll be better than the first measurements. Is it because they improved? No. It's because the measurements are inaccurate. You're making noisy measurements. So one way to say this is, the first measurements that you made, the x1s, those were not exact measurements of their true depression state. They were approximate measurements of their true depression state. They have noise in them. That's what N1 is in this problem. And so when you make these measurements, they have noise in this direction. But once you made the measurement, you forget about the fact that there was noise in it. You say, well, here's the measurement. This is the number. It's a number. It's not a number. It's a sample from a distribution, a measurement distribution. And if you then make another measurement, the new measurements will tend to be, they will revert to the mean. They will move toward the mean of the distribution. So this is true for any measurements. Basically.
It's also true for any sign, because the same energy drink is going to make happy children more depressed.
Exactly. Very important that if you were to take these folks over here that are happier than average and measure them the first time, you can take the first measurement, collect up the ones that are on the happy end of the scale, wait 3 months, measure them again, they're going to be a little more depressed. They're going down. These are going up. These are going down. Everybody goes toward the mean. So it's symmetric, it's balanced, everybody goes toward the mean. If you started out way above the mean, you're going to come down. If you started out way below the mean, you're going to go up. And there's nothing happening here, it's just statistics. It has nothing to do with the effect of the energy drink. And Kahneman, just to emphasize that point, says, it is also the case that depressed children who spend some time standing on their head or hug a cat for 20 minutes a day will also show improvement. Right? So you can have them do nothing, or you can have them do any random thing you want, and you will still see the improvement because it's just about the fact that you made a second measurement after you've made a first measurement, but you're conditioning on the first measurement. Okay. So this idea, this regression to the mean idea, is easily explained if you imagine the full measurement scenario that I gave you over here, that you've made two measurements of the same thing. Both of them have some noise in them. Let's assume they have the same noise in them, because presumably you're going to make this measurement of depression or whatever it is using the same measurement tool. You're going to have a questionnaire, or you're going to have some diagnostics, or you're going to have some device that makes, whatever it is, doesn't matter. Doing an MRI machine, it always has noise. All measurements are noisy. All measurements are noisy. So this fact that things go toward the mean is just built in to the process. And this is the kind of thing that does show up in newspaper headlines. People say things like this all the time, and it's false reason. This is not something that happens because there's a real effect there. It happens just because you're making noisy measurements. Okay, one more thing to say, and then we'll do a little bit of statistical decision theory. I want to complete something that we started, but we didn't finish. We started out, so first, let me remind you, an estimator is something that you compute on data in order to get something that you care about. There's some quantity that you'd like to learn, you made some measurements, you're going to compute something on the measurements in order to give you an estimate of the thing you want. You can make up anything you want for an estimator. It's just some function of the data. But in the language of statistics, and in the process of trying to formalize this and write down the right way to compute an estimator, the field of statistics has gone through a whole sequence of ideas, and they actually naturally build on each other. And we've already started that sequence. We started with maximum likelihood estimation, which looks like this. And this is, the notation in the math is always a little bit messy, but I think by now you should be used to this. So imagine D is a data vector, X is the thing that I care about. I measure, I conditioned on X, I have to describe the minimum from a statistical perspective, sort of mathematical statistical perspective. The minimum you need to build a proper estimator is a description of how the data relate to the thing you want. Kind of like, if you don't have that, then what is it that you're going to do? What do you compute? It's not obvious at all how to make up an estimator if you have no idea how your data relate to the thing you want. It's very common. The most common forms of estimation come out usually pretty simple, like taking an average, and that's because you're making direct measurements of the thing you want. Like, I want this quantity, the temperature, and I use a thermometer, which is made to measure temperature, and I make a measurement. And it's a little noisy, so I make another measurement. And it's a little noisy, and each measurement I make comes out a little different, and if I average them, I get a good estimate of the temperature. So that's the most common situation. And in that situation, it's like we don't need to think about any of this, because it's kind of obvious that the natural estimator is to just take the average. And we went through this process of sort of saying, well, if we do averages, why do we do averages? We talked about how to quantify the errors in the averages. But statistical estimation is much, much more general than that. And very often, and you will encounter these situations when you're trying to analyze your own data and think about your own experiments, very often the thing you're trying to estimate is not directly what you're measuring. You're trying to estimate some relationship between neural responses and behavior, and the thing that governs that relationship is not the thing you're going to measure directly. You're going to measure the neural responses, and you're going to maybe measure the behavior, but you actually don't know what the relationship is. So often the things you're trying to estimate are not the things you're measuring directly. And in those cases, the minimum that you need is to sort of express how do your measurements relate to the thing you care about. And that's what this is. This is an embodiment of how, if I knew the thing that I want to estimate, this is how I think my measurements would arise. This is, if you like, people in machine learning call this a generative model. It's a description of how the data are generated. Okay? And it includes both the probability distribution of the data, but it can also include like the relationship between the data and the thing, this X. This doesn't have to be that the data are just take X and add some noise, the way we described in our examples. This could be that it's take X, run it through some complicated nonlinear function, project it down to some funny space, and then perturb it with some noise that's not additive. So it could be a very complicated process. But whatever it is, you have to be able to express it here. And then maximum likelihood estimation says, given set of measured data, try to estimate x by maximizing this, okay? Or minimizing the negative log likelihood, right? You take the log of this and you negate it, you minimize that. All right. Then there's map. We've done that the last 2 lectures. We talked about map, maximum a posteriori, and basically that's Latin for estimate, flip the probability around, get the posterior distribution, not the likelihood, get the posterior, and then maximize that. So that's just, it looks the same except that I flipped, right? This is P of x given D, and we do that by introducing a prior. So the point of each of these steps is going to be that we're going to add a new element. We have to assume something else, a more complicated model, if you like, by adding one more element in order to achieve each of these steps. Okay, so the first step is I need the likelihood. That's the generative model. I've got that, I do this. Okay. If I think I can make up a prior, or I think there's a prior that makes sense for my problem, or this one that's very natural, I might include that. Once I've got the prior and the likelihood, I can combine them. I get the posterior, and then I do this. We just went through a bunch of examples like this. But we're actually not done. There's one more thing that you can add to the problem. And it seems, often, I think, to students in your position, it seems like unnecessary, like why would you bother with that? So I'm going to try to just give you some intuition. The last thing you can add is, these things are probabilistic, right? This is the probability of observing data given x. This is the probability that a given x could be the true x, given that I've observed the data. So this is using Bayes' rule to flip things around, a kind of more sensible configuration. But we can keep going. This thing says, find the maximum, the most probable x. But very often, when you're trying to solve estimation problems, this comes up all the time in engineering, and as we're about to see, this comes up even in perceptual studies and models of perceptual studies. What you want is to actually take into account the kinds of errors that might get made when you make your estimate. And you might actually want to consider a situation where some of those errors are more costly than others. So the standard example of this would be something like, I want to estimate how far it is to the edge of a cliff. What I would like to do is to walk up to the edge, and I want to have this fantastic view, and I want to see as much as I can. So I want to get as close to the edge as possible. That's my goal. And my goal when I'm back here is to estimate how far is it to the edge. In this situation, and I could just go ahead and let's say I make some measurements and I do a map estimate of how far it is to the edge. But I say in this situation, my estimate of how far it is to the edge, I don't want to maybe pick the most probable, because I really care a lot about, there's kind of these errors that I can make that have to do with, if I estimate that it's farther away, if I estimate that it's closer than it really is, well then I won't get as close as I want, and I won't see as much. That would be kind of disappointing. But actually much worse is if I estimate that it's farther away than it really is, then I'm going to walk off the cliff. Okay? So this is really bad. So you see there's an asymmetry. This has nothing to do with the probability. This is about the asymmetry of what it's going to cost me to make mistakes. Like it might be much, much worse to make that one mistake, a mistake on this side, than it is to make a mistake on this side. So what I need in addition, and I can't get any of this out of the probability. The probability doesn't tell me about the cost that I'm going to incur if I go with that estimate and I get it wrong. So what we can introduce to complete the story, and this is mostly so that you understand that this is the landscape of the full problem of statistical estimation includes this one more piece. So far we have two pieces. We have this likelihood. I call that a generative model. We have to put in a prior to convert that into a posterior. So that's two pieces. There's one more piece, which is called a loss function. Sometimes it's called a reward function. It's basically, or a cost function. It's the thing that expresses how much is it going to cost me to make mistakes. And if that thing says that some mistakes are worse, much worse than others, then I should take that into account when I make my estimate. I should try to make that, and this basically happened in the early days of probability. People realized that this could be important, and it became really important in real engineered systems. So imagine you're doing radar processing in World War II, because this is where it really became a big deal. and you're trying to figure out whether the funny little smudge on the radar is an airplane or it's just some sort of artifact or a piece of noise or some other, you know, a cloud or whatever, some other, a bird, right? You have to make a decision. It's a binary decision. So you have a model for your measurements. That's this. You have a prior, which is that airplanes are not very common. Most of the time when I see stuff coming on the radar, it's not an airplane. So that's the prior probability of an airplane versus not an airplane. It's much higher chances of, it's not symmetric, it's much higher chance of no airplane. And then there's one more thing, which is the cost of making mistakes. If I think it's an airplane but it's not, that's one kind of mistake. And then there's another kind of mistake, which is there is an airplane but I don't notice it. And if you're thinking, you know, wartime, which is where this all got developed, making that second mistake is really bad. That's Pearl Harbor. So that's really bad. You don't want that mistake. So you have to weight the two kinds of mistakes. You say, if I have what's called a false alarm, if I think there's an airplane and there's not, that's not great, but it's not nearly as bad as the other one, which is called a miss. I missed the fact that there was an airplane. So what you do is you put in, you make a loss function, you express how much is it going to cost you to make these mistakes. And now what you want to do is not maximize probabilities. You want to minimize the expected cost or loss, right? So what you have to do is you express the loss. This is how much does it cost you to make this estimate when the true thing is this. The loss is a function of those two variables. Usually it could be a function of the two independently. Here I wrote it as minus. So there's a loss function. And then you condition on the data and you compute the expected value. That is, you take this thing and you integrate it against the probability of the true thing given the data. So now we're integrating over the probability. We're not finding the maximum. That's what we did here. We are integrating over it. We're computing an expected value. That's an integral. Or it could be a sum if it's a discrete distribution, but it's generally an integral. So we're going to compute the integral over this thing and find the x hat that maximizes that. So that's a general, that's called a Bayes estimator. When somebody says they're doing Bayes estimation, they actually mean that. I'm minimizing the loss over the posterior. And then there's a special case, which so that terminates our three ingredients. There's three ingredients. There's the likelihood function, there's the prior, and there's the loss. And I'm putting them in that sequence intentionally because each of them, if you start with just the likelihood function, you can still do estimation. That's maximum likelihood. If you've got the likelihood and the prior, you can do map estimation. And if you've got a likelihood and a prior and you have a loss, then you can do this. Okay? Full Bayes estimation. And there's one special case that's listed here because it's worth knowing about. If your loss function is squared error, the squared error, then actually the best estimate is, you kind of can guess this. What is the thing that minimizes squared error? It's like where we got to when we started talking about central tendency and dispersion. The thing that minimizes squared error is the mean. So the answer here is the mean. But and that's kind of a nice special case, right? If you use squared error, you get the mean. Notice that this is not the same as the map estimate in general. This thing says take the maximum of this distribution. This thing says take the mean expected value of this distribution. If the distribution is a Gaussian, well, those are the same. A Gaussian is a symmetric distribution. The mean is the same as the maximum. It's in the middle, right? If I have a distribution that's not Gaussian, like it's asymmetric, it kind of goes up quickly on one side and then it has a long tail on this side, well, now the mean is not the maximum. They're in two different places. So these things can be the same. In fact, all three of these can be the same under some conditions, but they're not always the same. And in cases where they're different, it can actually really matter. So this thing, computing the mean, it's a very natural thing to do. And it's not necessarily the same as this, except if you've got Gaussians, then these two things are the same. And you might as well just think about doing this, right? So you can kind of see. And in fact, if your prior is flat, uniform, then multiplying the prior by the likelihood doesn't do anything. The prior times the likelihood still looks like the likelihood, and then these two things are the same. In fact, often people say when they're doing maximum likelihood estimation, they say, well, I'm doing map estimation, but I'm assuming the prior is flat. Because matrix that map estimation turns into maximum likelihood. So these things are related to each other, and they're even the same under some conditions, but there are always conditions where they're not the same. And when they're not the same, putting in these extra ingredients can really make a difference and can give you a better estimate. There are many, many, many cases in engineering, in engineered systems, machine learning systems, things that are trying to optimize various things, where doing this, or even full Bayes for a non-symmetric funny distribution, is much, much better than doing this or doing this. So if you have the right information and you know how much it's going to cost you to make errors, you really want to do this. This is the right thing to do to minimize your costs. Okay. This also shows up in economics. It's utility theory, where you assign costs for utility. They usually think of it in a positive way. Utility is a positive thing. You want to maximize utility. It's just flipping the sign, right? Maximize utility, minimize loss. It doesn't matter which way you describe it. Okay? But it's the same idea. What you do is you maximize the expected utility, minimize the expected loss. Okay? All right. So with that in mind, let's do just a little bit. So now I really am down to the wire. It's a great show, The Wire. How many of you have seen The Wire? A handful of you. If you want to see the greatest thing ever created for television.
It's like the best show ever.
So you're watching right now? Season 2. Season 1 is amazing.
Homework 6.
Good. All right. No more advertising. All right. So what we want to do is go through what could be called, well, we'll call it SDT, which could be this or this. It's this if you're thinking of mathematical statistics and the development that has been done throughout engineering of how to make decisions optimally. And it's this if you're thinking specifically about the case of detecting something, binary detection, is the plane there or is the plane not there? Or if you want to flip to something a little bit more biological, is the tumor there or is the tumor not there? Or if you're doing human perception, is the stimulus on the screen or is the stimulus not on the screen, right? So this becomes a way of modeling human behavior and also analyzing data from human experiments. It's also the way that we would process radar images or process medical X-ray images or lots and lots of other things. Okay, so this is a fundamental set of tools, and they're all built on all the tools we've already got. In fact, we've already, that last slide about those statistical estimators is all you need to really understand all of this. Okay. All right. I just told you that. There's an MRI. I think it's an MRI of David Eager's brain. Yeah, those of you that are interested, there's his name on the from back when he was at Stanford. Imagine you're trying to figure out if there's a tumor there or not, or you're looking for, you're trying to make some measure of his intelligence, or, okay, let's not do that. So here's the way you set up this problem, okay? It's an estimation problem, like what we've been talking about all along, but now the thing we're estimating is binary, okay? That's why it's a decision as opposed to a sort of general estimate. Think of it as the variable that we care about, the x in most of these slides, although in this one it was c. The x that we care about is a binary thing. It could be yes or no, or it could be A or B, or it could be the thing is not there, we'll call that 0, or the thing is there, we'll call that 1. Whatever it is, it's discrete and there's two options. That's a decision, okay? So we'll in these slides, we'll label it as N and S, the two cases, where N means you're just looking at noise, and S means you're looking at signal. It's usually going to be signal plus noise, okay? And so we can imagine a distribution of here, I guess, sorry, the X now is not going to take the role of the measurements, as maybe luckily, as it was when we wrote this out. This thing was, I told you, imagine there's a variable z that we're trying to estimate, and the x's are our measurements. That's how we set this up. That's what cx was, our measurement distribution, right? Okay, so now x is the same thing here. X is a measurement. It's noisy. There's a true thing, which is a variable that takes on either the value n or the value s. It's a binary variable. Okay, it doesn't matter if you call it 0 or 1 or n or s, because we're always just going to lay out the two discrete cases. If it's equal to s, then you get this distribution of noisy measurements. And if it's equal to n, you get this distribution of noisy measurements. It doesn't matter where these are centered. They're just different, okay? And that's what you have to base your decision on. You, the person or the machine or the brain that is receiving these measurements could be like noisy responses of a neuron. You have to make a decision about what's out there based on that noisy measurement. So you look at this picture and it's kind of obvious what you should do. It's intuitive, right? If I make a measurement over here, what should my answer be? N or S are your choices. Probably N, right? And if I make a measurement over here, probably I'm going to say S, right? And if I'm somewhere in the middle, now it gets harder. It's not clear, but if you have to decide, you're probably going to do something like, well, I don't know, pick the one that has the higher curve. Like, here's the intersection point, and maybe to the right of that I'll say it's S, and to the left of that I'll say it's N. It's kind of obvious just looking at the picture. If I forced you to figure out an answer without doing or thinking about any math, but you understood that these curves are probability distributions over the measurements, you would arrive at a solution which actually is the maximum likelihood solution. So what's maximum likelihood here? Remember how we do this? We write down the measurement probability. Well, that's what this is. We usually think of a single p of x given the true thing. We call it theta in the early examples. And theta here is binary. It's equal to n or s. And so the maximum likelihood means maximize p of x given theta over theta. But maximize here is not like I don't take the derivative and look for the peak. Maximize here means, well, I only have two choices. Theta is equal to n or it's equal to s, so I have to choose. And so you just look at those two values and decide which one's higher, i.e., you look at these two curves and you decide which one's higher. And that's the answer for each x. So, let's see, do I have it on the slide? Yes, I do. Here's the answer. The estimator is, we call it a threshold estimator, because it draws a line along, it draws a boundary along this x-axis, it's right here, actually at the place where the curves cross, and it makes a decision. The decision rule is a threshold rule, which says if I'm above the threshold, pick S, and if I'm below the threshold, pick N. And that is the maximum likelihood rule. Okay. And when you have equal shape distributions, they're unimodal, they're symmetric, the decision rule is always a threshold. Okay. Just to be clear, it doesn't have to be a threshold, or it certainly doesn't have to be a single threshold. And if I had more complicated distributions, I can easily imagine situations where, I guess I should do these in two colors or something. Let's pick green and red, blue and red. You know, it's easy to imagine that a situation where, you know, the distributions do something a little more complicated. There's one distribution, and maybe the other distribution does something funny like this. And now what's my decision rule? What's the matter? Are you stretching or are you raising your hand?
I was turning the camera to the other board.
Okay. So now what's my decision rule? It's the same decision rule. It's still maximum likelihood. I just pick the curve associated with the highest, the curve from the one that has that's highest, right? So that means that to the left of this boundary, I'm going to pick the blue thing. So I'll pick blue here. Sorry. And in this little interval here, I'll pick red. And in this interval, I'll pick blue. And then from then on, I'll pick red. So now I have something that kind of switches back and forth, right? So I've got blue, and then I've got red in here, and then I've got blue in here, and I've got red in here. So my decision rule is no longer a simple threshold, it's kind of multiple thresholds, right? If I'm in this interval going to the left, go with the blue one. If I'm in here, I'd go with the red one. If I'm in here, I go with the blue one. If I'm in here, I go with the red one. So it's not guaranteed that the maximum likelihood rule is a threshold rule, But in simple cases, like this is Gaussian, it is. Just to be here, this one's, you know, kind of quirky and weird, right? Those distributions are kind of nutty. But let's do a more realistic case, actually. Let's imagine I make two measurements, that under these two conditions, the noise is different. Let's imagine that it's Gaussian in both cases, but it's different Gaussians. Okay, so again, I guess I'll do blue and red. So when, in one case, I get a measurement like that, whoops, and in the other, I'm using the blue one, this is like, the green one rather, it's clearly visible. Can you see this? I should ask the camera, can you see this? I'm sure not. Damn markers. Okay. Let's say it looks like that. And these are both Gaussian. They're nice single unimodal lumps. There's nothing weird like there was in the previous one. Well, now, again, I don't get one threshold, right? These curves cross here, and they cross here. And you can see from the picture that when I'm in this middle range, I'm going to pick the red one. And when I'm outside of that middle range, well, I'm going to have to pick the green one, right? Because that's the maximum likelihood rule. Pick the one that's highest likelihood. Okay? All right. So, maximum likelihood says, compare the two curves, pick the highest one. In simple symmetric cases like what's on the board, it comes down to a single threshold. In general, it is probably multiple thresholds. But that's the rule. And now we can ask, just to connect that rule with like errors, right? When am I making mistakes? Well, generally, you're making a mistake whenever you say it's one thing, but it's actually the other thing. And the way you calculate the chances of making a mistake are kind of like this. So this diagram lays it all out. It's a little bit hard to look at, I'm realizing. It's just like making me a little crazy to look at this. I can't look. Must be something about the stupid screen. It's another chance for me to make it to bust on the screen. Yeah. Okay, so here's the same picture that we already had. And it's just the same picture replicated because I'm splitting it into these two cases to lay out four different possibilities. Why are there are four possibilities because it's a binary variable, and there's what the true thing is. This is in terms of tumor detection. So tumor present versus tumor absent. So think of that as this is S and this is N. That's the true value of S or N, right? And then there's our estimate, or the doctor's estimate. The doctor says no, that is, the doctor says N, and the doctor says S, right? So I have these four cases. What is the true thing, and what is the answer that is given by the estimator? And I can think about these four cases, and what do these four cases correspond to back in the probability diagram? Well, it's pretty simple to work through. So I'm making a threshold here. I'm going to say S when I'm to the right of this threshold, so I can kind of consider all the stuff that's hashed in green. The stuff that's hashed this way in green is going to correspond to situations where I drew a sample from this, that is, it really was S, and because I'm to the right of this threshold, I say it's S. So rightward green hashes, leaning right, is this corner, and we call that a hit. We have a name for that. That's a hit. I actually hit the target. I got that. There was something there, and I got it right. I said that it was there. I saw it, or I estimated it properly. To the left is the situation, and the red hashed to the left is the situation where it did come. The S really was there, but I'm now to the left of this threshold, so I say, oh, it's not there. We call that a miss. The thing actually was there, and I said it wasn't. So I missed. That's this corner. Okay? And then down below, we could put these all in the same diagram, but it gets too messy, so let's just split them off. Down below is the true thing is not there, the N. Okay, so I'm drawing from this distribution, the left distribution. And to the left of the threshold, I say it's not there. It's not there, and I say it's not there, or my estimator says it's not there. So that's a correct reject. I correctly reject this. I correctly say there's nothing there, and that is correct. And then there's another kind of error. That's the false alarm, right? Which is, it's not there, but I say that it is. I hallucinate. I say, yeah, I think it's there. Why do I say I think it's there? Because I made a large measurement of x. It's an unlikely thing. It's coming from this tail of this distribution, but it can happen. So I happen to draw a sample from this tail of the distribution. I say, oh yeah, it's above the threshold, so it must be there, but it's not. Okay, so that's the false alarm. 4 possibilities. We have names for these. These are conventional names that come from signal detection theory back in the 50s. You know, the names are a little annoying. Some of them are short, some of them are longer, some of them are 2 words. It's kind of annoying. There's no symmetry here in these names, but those are the standard names. But really all they correspond to is the integral under these curves to the left and right of the threshold. And there's 4 numbers that correspond to the 4 possible integrals. The integral to the right of the threshold, the integral to the left of the threshold for each of the 2 curves. Those are the 4 numbers. And how do you get the integral under a probability distribution? Does that correspond to anything we've seen? Right. Okay. The cumulative is the integral. It's the sort of the rolling integral of the probability distribution. So in fact, these left tails are just equal to the cumulative of these distributions. And the right tails are, well, it's the stuff to the right, so it's going to be 1 minus the cumulative. So you can actually calculate these 4 numbers by taking the 2 cumulatives and just measuring the value of the cumulative and 1 minus that. And that already tells you that these numbers are not sort of independent numbers. One of these is 1 minus the other. Okay. All right, we're out of time, but the rest of this is just to point out, is to think about how the errors and the correct answers balance out as a function of what these curves look like. And in particular, you can kind of already have the intuition. The amount of error, the stuff in these red regions, just is really going to depend on how overlapping the 2 curves are. If these 2 curves are way, way, way apart, here and here, there's very little overlap, then you don't make any mistakes. And if these curves are very, very overlapped, then you make a lot of mistakes, because this stuff is going to be really big when they're overlapped. And that's basically what it comes down to. You can do, and the calculations that you do to calculate what the probability of errors turn out to be something that you can't do in closed form. You actually, they involve integrals under the tails of things like Gaussians, and usually you're not going to be able to write those in closed form. But you can still have the intuition about how they're going to behave as a function of how far apart the distributions are. Okay, so Mike's going to work through a bit of that next time and show you how to connect the 2 central functions. See ya.